first of all, like always, thanks to the organizers for giving me the opportunity to speak, and thanks to all of you for still being here. I'll try to be not too long. So this is sort of an add-on to Christian's talk from yesterday. I'm going to try to explain this twisted string algebra, or maybe better work with the modified string algebra that we use to realize the non-invariance of the string, and also use in the six-dimensional superconformal theory. I should say that most of what I'm going to say is based on the work by Schreiber and Society and and other people, but mainly one of their papers from 2008. All right, so just a quick reminder of what the story was. So we were looking at this self-Lewis string equation, which is a higher analog to the monopole equation. So it's just some free-form curvature H, supposed to be equal to Hodge phi in 4 dimensions. And this curvature takes values in an infinity algebra, which we've now seen a lot, so I'm not going to define a lot about it. And as Christian tried to convince you, a good candidate for a good infinity algebra is the string D2 algebra, which comes in 2 different models. One of them is the skeletal one, which is kind of like a central extension. We just have the algebra in degree 0 and R in degree 1. And then there's an equivalent model, which is called the loop model, which is based on the path group and the central extension of the loop group on the algebra. All right, so there's this thing which I also want to mention, which appears all over in higher gauge theory, which is called the flatness condition, or the curvature condition, which is just so okay, this is a free-form curvature, but we of course also have a two-form curvature f, and this oftentimes has to be 0, for example, for a consistent parental transport and all these kinds of things. And this also appears in this story in 2 different guises. If you look at these things and work out the gauge transformations of H, you see that it depends on F. So that this equation up here is only gauge covariant if F is 0. And another thing is, if you look at the categorical equivalence between these, I mean, if you write down the quasi-isomorphisms, you see that H transforms like this, where phi naught and phi 2 are part of this isomorphism. So this also depends on F. So unless F is 0, this again destroys that equation, which is not good. So we would expect to need F equal to 0, but that is, again, that is also problematic because this essentially forces us to the abelian case, and we want to look at non-abelian solutions to this. So this story is basically about what you can do to lift this. All right. So yesterday, Christian gave you basically a lightning review on high gauge theory. So I want to let's say a little bit more about this. So I guess consider this the thunder review. That's a little bit later, but a little bit longer. Okay. So like you already told me, you can formulate all of higher gauge theory in morphisms between differential algebra, which is a very nice picture where basically all the information you need is encoded in such morphisms. And what you look is, you give them some infinity algebra, you take the Chevalier-Allenberg algebra, and take a morphism out of that to the Durham differentials of an handful X, and that gives you potentials and flat curvatures. And homotopy between such morphisms give you gauge transformations. And just so we don't lose ourselves, just give you the simplest example of an ordinary Lie algebra. So you have just one generator, which is called T alpha in degree 1. And then you have some derivation on the Chevalier-Allenberg algebra, which is basically just a dual of the T brackets, so these F are the structure constants. And then you can take a morphism that's degree preserving to the arm complex, so I map T alpha to the connection 1 from A. And then, because such a morphism should respect the differential, this cube basically becomes D, and then this equation just says that dA plus a half AA is 0. Which is just saying that the curvature is flat. So this is why I'm saying this encodes only flat curvatures. I mean, that's nice, but we want to do it for general curvatures that can be non-flat, and this is where we need a new concept, which is that of the Weil algebra, which is Christian mentioned. So what is this exactly then? So it's basically a doubling of the Chevalier-Allenberg algebra. So you take your G and copy it and shift it by another degree. And then you define a new Q on this differential algebra, which is the old Q plus the shift isomorphism that identifies the generators in here with the generators in here. And just by requiring this and saying that this should square to 0, this also gives you Q on the shifted copy, which is given by this. So what does this look like? In our example of a normal algebra, now we have two generators, one in degree 1, one in degree 2, which is the shifted one of this. And Q on T is just the old Q plus the new shifted copy. And then using this, we also get what Q on R should be. So what does this do? I mean, this is just a nice trick. So I mean, it's the same slide as before. The only difference is now we're looking at morphism coming out of the Weil algebra instead of the Society-EPSRC algebra. And now this encodes me any curvature LA, and conveniently also gives me all the Bianchi identities quite quickly. So if I just look at the same morphism as before, and I have T and R, T still gets mapped to A, R gets mapped to the two-form curvature F. And this equation maps over to just F is dA plus a half AA, which is the normal expression. And then the Q on R just translates to the Bianchi identity, so lambda F 0. Right, okay, so far so good. So we're going to need a third concept which is related to this and relevant to the story, and that's that of the invariant polynomials, which in this picture are just the elements in the Weil algebra that sit entirely in the shifted copy, in the new one we added, such that Q on that element is again completely in the shifted copy. And we consider two of them to be equivalent if they differ by an exact term. I mean, Q of something that's also completely in the shifted copy. And then the algebra of, I mean, the equivalence class of those we call inf G. And this is just to make a connection with normal stuff. This is for normal algebra, precisely the characteristic classes that you usually identify with a I mean, these get identified with the characteristic classes in Schönlein view. So it's essentially, you know, traces and debts and then F's put into there. And this, these invariant polynomials, together with the Schönlein algebra and the Weil algebra, form a short exact sequence. I mean, this sits inside here, and then the Weil algebra projects down to C of G. And this is the short exact sequence that will be relevant. So you can do it a little bit better, be a bit more precise, and define what is called a G connection object. So this is essentially a diagram of this form. So on the right here we have this short exact sequence. Here I have my morphism coming out of the Weil algebra to now, okay, P is a principal bundle over X, so I now look at the total forms on the principal bundle. And then the commutativity of this first square essentially is implied by the first Ayres-1 condition of the connection on the principal bundle, which says that on the vertical directions, I'm just the Maurer-Catan form, and this is essentially saying that this morphism on the vertical part factors along the Schiller-Allenberg algebra, so that its curvature along that part is 0, which is true for the Maurer-Catan form. And then this bottom square, the commutativity follows from the second Ayres-1 condition, which is just the normal statement that the characteristic classes pull back to form global forms on the base notebook. Yes. No, that's I should make it. Okay, so then the question that's going to lead us to this modification is, can I, given such a G connection object, lift it to, I mean, for the algebra G, lift it to the corresponding skeletal string structure. So can I get this morphism and factor it along here? And the answer in general is no. But what you can do is instead look at this at infinity algebra, where you put another copy of R in degree 2 on there. And this comes with the canonical morphism going from here to here. And then, of course, you can, and then essentially the part that sits in here is the obstruction to lifting it to the string algebra. But the point now is, what's going to be important for us is that now I want this whole thing to commute as well, and the subtlety here is if you follow the generators in here and want to make this commute, this forces you to slightly modify the Weil algebra. And this is exactly the modification that Christian was talking about. So let me just quickly show you what exactly that does. So for the skeletal case, I have this algebra, and I mean these are the normal curvatures and Bianchi identities I would get. And this kappa alpha f is the new term that I get additionally, where kappa is the killing form of the algebra. So these two things cancel out to give me a Chern-Simons term. And now I have basically the Contiagen sitting here. And this has the effect that in the in these gauge transformations of H, the dependence on a f vanishes. So now you can have H equals to Hodge d phi independent of what f is, so you don't have to impose the fake flatness condition anymore. And then the new thing is that you can also do this in the loop model. You do an analogous diagram, you put this in there, you force it to commute, and this introduces new terms, which formally looks pretty much the same way, but now kappa is some new function, which is, I mean, it's not the killing form, okay? And then, again, this solves the problem with the gauge transformations, and also now, because you've now done it in both models, the categorical equivalence also loses its dependence on f. So you can now map equivalence classes, gauge equivalence class of solution in one model to the other and back, and it works nicely without having f equal to 0. And that's basically the story, and there's more to be done here. So, I mean, you can try to do this with other structures. So one of the things we want to do now is, I mean, this is the algebra down here that we did before. But for the 6-dimensional model, we need a notion of inner product, and this doesn't exist here, so you need to minimally extend it and double it, this whole thing. And so that the whole thing on homology essentially is just G. We also need another candidate here. And then you do the same procedure, and that should lead you to expressions for the curvatures that you have. And those now slightly disagree with what some being testing and Durham got in their model from tensor hierarchy. So this is why we're working on this now, and then trying to redo the whole calculation. And that's all I want to say.
One quick question. It's not a question, but another gentleman saying.
I just want to make a comment. This is very nice. I just want to amplify that it's hard, the way you state it sounds a bit like something doesn't work, so you do something different, just ad hoc. And I just want to say, the whole thing, these diagonal maps are quasi-isomorphisms. You have the freedom, and they are still up to you. So you have that freedom to change it, because you have the freedom to change things up to equivalence, because you have homology theory. And so you have the freedom to pass to a good model, and that's what you do.
Yes.
Just to amplify that this is not, you're not saying, oh, it doesn't work, so you do something different.
Okay.
Right?
Yeah.
But isomorphism of these three things, all of the three are quasi-isomorphisms. So you have, and the Weil algebra is contractible, but if you wanted to sit in that diagram, you have the freedom.
No, I agree. It's not just a quasi-isomorphism.
So you have this equation H is star H is d phi.
Yes.
And I guess that's a covariant derivative of d phi.
Okay, so that's the yes, that's the equation in the skeletal case where the covariant derivative is the same as the little d because the mixed mu2 vanishes. But yes, in general it is.
So what's the equation that determines f and a, the gauge field?
Okay, all I wanted to say here is that you don't necessarily have f equal to 0. So what we ended up having is f equal to I know what we ended up having is f equal to Hodge f, which are the instantons things that Christian mentioned, which then you can find globally defined solutions for these equations. Yeah.